You know how your phone can translate a sentence almost instantly? Well, a huge piece of that puzzle snapped into place back around 2014. That's when machine translation took this incredible leap forward. And it wasn't just because of more powerful computers. It was because of a totally new way of thinking that, believe it or not, taught machines how to pay attention. So we're going to trace the story of that breakthrough. We'll start with the brand new idea for how to do translation, then we'll hit the major roadblock that almost stopped it in its tracks, and finally we'll get to the genius solution that pretty much changed AI forever. We'll even peel back the curtain on how a machine can understand a word to begin with. All right, let's dive right in. Now, to really get why this new idea was such a big deal, you first have to understand what the old way of doing things looked like before 2014. Okay, this slide really lays it all out. On the left, you've got the old school method, statistical machine translation, or SMT. Think of it like a giant, complex Rube Goldberg machine. It had all these little separate parts and statistical tables that humans had to build and then tune by hand. It was complicated. The new idea, neural machine translation, said, let's throw out that whole machine and replace it with one single, big neural network. Let's just show it a ton of examples and let it figure out how to translate all on its own. And this new approach was built on this really elegant framework called the encoder-decoder. It was laid out in a super influential paper back in 2014 by a team that included Ilya Sutskever. The process is actually beautiful in its simplicity. You have two parts. First, an encoder network reads the sense you want to translate, say in English, one word at a time. Its only job is to squish the entire meaning of that sentence down into a list of numbers. Then a second network, the decoder, takes that list of numbers and unpacks it, generating the translation, maybe in French, word by word. And that single vector of numbers that gets passed from the encoder to the decoder, that is the absolute key. It's sometimes called a thought vector, and the idea is that it holds the complete meaning, the entire vibe of the original sentence. It is the only thing the decoder gets to see. And here's a fun little detail from their paper. The team found this weird trick. If they just reverse the order of the words in the original sentence before feeding it into the encoder, the model got way better. It's a simple hack, but it made it much easier for the network to connect the dots between the start of the input and the start of the output. So this encoder-decoder model was a huge step forward, but it wasn't perfect. In fact, almost right away, another team of researchers, including Dmitry Bohodnow and Yoshua Bengio, spotted a major flaw in the design. They asked a question that seems obvious in hindsight, but was a total game changer. They asked, hey, can a single fixed size vector really be expected to hold all the meaning of a super long and complicated sentence? I mean, think about it. Trying to cram the nuance of like a 50-word sentence into one little package of numbers? Something's got to give. And here's the crucial point they made in their paper. They basically said, look, we think this fixed-length vector is a fundamental bottleneck. It's like trying to force a river through a tiny pipe. The longer the sentence, the more water, the more information you're going to lose. It just wasn't going to scale. And this chart shows you the problem in plain sight. It plots the translation quality against the length of the sentence. Now look at that lower line, which is the standard model. It does great with short sentences. But as soon as you get to longer ones, the quality absolutely falls off a cliff. The bottleneck wasn't just a theory, it was real. So if that's the problem, what's the solution? Well, this is where things get really clever. Instead of trying to cram everything through that one tiny bottleneck, they asked a different question. What if we just let the decoder look back at the original sentence? And this was the big idea behind the attention mechanism. For every single word the decoder is about to write, it gets to look back at the entire input sentence and decide for itself which of those original words are the most important for figuring out this one next word. It learns to pay attention to what matters, right when it matters. To really see how this works, let's take a look at a classic translation challenge. You've got the English phrase, the European Economic Area. In French, that becomes la zone économique européenne. Now, you can spot the problem right away, right? The word order is all jumbled up compared to the English. The adjectives come after the noun. A simple linear translation would completely mess this up. But this is where the magic of attention comes in. The model learns that to produce the word zone, it needs to pay attention to the word area. Then, to produce économique, it shifts its focus all the way back to economic. And for européenne, it looks back at European. It learns to jump around and connect the right words, no matter where they are in the sentence. It's brilliant. So, we've been talking about how the model processes these sentences. But that kind of begs a deeper question, doesn't it? How does a computer even know what a word like European or area is? It's just letters to a machine. Well, the secret sauce here is a concept called word vectors, or word embeddings. The basic idea is that you turn every single word into a list of numbers, a vector. And you do it in such a way that in this giant, high-dimensional meaning space, words that have similar meanings end up being close to each other. So how does a computer learn these relationships? Well, models like one called Glove basically read a huge chunk of the internet, and they just count how often words appear near each other. For example, as this table shows, the word ice is way more likely to show up next to solid than the word steam is. By looking at the ratio of those chances, the model learns that solidness is related to ice and gasness is related to steam. And what you end up with is this mind-blowing vector space where you can actually do math with concepts. You can take the vector for king, subtract the vector for man, add the vector for woman, and the point you land on in this space is going to be closest to the vector for queen. It's incredible, and this is the foundation that lets these neural networks understand language at all. All right, so let's zoom out and pull all of these pieces together, because what happened here wasn't just about making a better translator. It was the start of a massive revolution in AI. What we've really seen here is this amazing journey of discovery. First, there was the breakthrough idea, the simple encoder-decoder. Then, someone found a critical flaw, the long sentence bottleneck. And that led to an even more powerful solution, the attention mechanism. And of course, the whole thing is built on that bedrock of word vectors, which gives meaning to the machine in the first place. And here's the biggest takeaway. Attention wasn't just a patch. It became a core, fundamental building block for AI. This idea of letting a model dynamically focus on what's most relevant, it's now used everywhere. In systems that write captions for images, that summarize articles, and yes, in the huge large language models like GPT that are changing our world. So, this incredible journey, all starting around 2014, leaves us with a pretty fascinating question to chew on. We taught machines how to pay attention to human language, and that unlocked all these incredible abilities. So, what happens when they learn to pay attention to everything else? What new capabilities will that unlock?